apologise. I'm sure you are aware we have a technical issue with our number 2 engine. We have dealt with the situation at the moment. The aircraft is secure at this stage. We're going to have to hold for some time whilst we do lighten our load by dumping some fuel and a number of checklists we have to perform. But as you can, I'm sure you are aware, we're not proceeding to Sydney at this stage. We're making our left turn now to track back towards Singapore. And as we progress with this, we'll keep you informed. At this stage, everything is secure. The aircraft is flying safely, and we'll get back to you very shortly with further information. Thank you for your patience.
On November 4th, 2010, Qantas Flight 32, an Airbus 380 with 440 passengers, 5 flight crew, and 24 cabin crew, departed Changi Airport, Singapore, on a scheduled flight to Sydney, Australia. About 4 minutes after takeoff, while the aircraft was climbing through 7,000 feet over Batam Island, Indonesia, the flight crew heard 2 bangs. A number of warning and cautions were displayed on the Electronic Centralized Aircraft Monitor, or ECAM. Initially, the ECAM displayed a message, warning of turbine overheat in the number 2 engine. The crew was cleared by ATC to conduct a holding pattern to the east of Changi Airport. While in the holding pattern, the flight crew worked through the procedures relevant to the messages displayed by the ECAM. The aircraft had sustained significant impact damage to the left wing by fragments and debris from the uncontained engine rotor failure, and fuel was leaking from the damaged left wing fuel tanks. The flight crew reported that during their assessment of subsequent multiple fuel system ECAM messages, they elected not to initiate further fuel transfer as they were unsure of the integrity of the fuel system. In addition, the flight crew could not jettison fuel due to damage to the fuel management system. After completing the ECAM procedures, performing some aircraft controllability checks, and determining the landing distance requirements, the flight crew landed the aircraft safely at Changi Airport. After landing, fuel continued to leak from the left wing tank. The risk associated with fuel leakage near hot breaks was minimized by airport emergency services, who applied large quantities of water and foam below the left wing while the aircraft's engines were shut down. The number 1 outer left engine continued to run following the normal shutdown procedure. Because of the still running engine and leaking fuel on the left side, the passengers were disembarked via a set of stairs on the right side of the aircraft. The disembarkation was completed about 2 hours after the aircraft landed. The number 1 engine was finally shut down about 3 hours after the aircraft landed by pumping firefighting foam directly into the engine inlet. There were no reported injuries to the crew or passengers, and there were no confirmed injuries to persons on Batam Island. The Trent 900 is a 3-shaft high bypass ratio turbofan engine with variants ranging in maximum thrust from 75,000 pounds to 84,000 pounds. The 3 primary rotating assemblies in the Trent 900 are, first, a low-pressure or LP compressor connected by a shaft to a 5-stage LP turbine, second, an intermediate pressure or IP compressor connected by a shaft to a single-stage IP turbine, and third, a high-pressure or HP compressor driven by a single-stage HP turbine. Each rotating assembly is supported by bearings at the front and rear of each shaft. The number 2 engine on Flight 32 was a Rolls-Royce Trent 972-84 variant. The engine's rated maximum takeoff thrust was approximately 76,800 pounds. Spaces within the IP turbine module are supplied with compressed air from various engine compression stages to provide cooling or sealing functions. The Trent 900 is of modular construction and includes a separate module for the IP turbine. The HP IP bearing support structure provides radial and axial location support for the HP and IP bearings. The bearings are located in a hub structure that encloses an oil-fed bearing chamber. That hub is connected to the IP turbine case through a strutted ring structure that has a front and rear panel. The support struts pass through the IP turbine nozzle guide vanes. The oil feed, scavenge, and vent pipes pass through clearance holes in the outer hub, then through the buffer space and secured to the inner hub by an interference fit. An integral filter in the oil feed stub pipe was included, with the intent of preventing oil contaminants entering the HP-IP bearings. To accommodate the filter in the oil feed stub pipe, the inner hub end of that pipe has an enlarged inside diameter. A number of oil feed stub pipes within the HP-IP hub assembly were manufactured with thin wall sections that did not conform to design specifications. The non-conforming oil-fed stub pipe on the number 2 engine developed fatigue crack, which led to an internal oil fire. The leak was at a low rate, but at a pressure that likely resulted in an atomized oil spray. The temperature in the buffer space was reported by the manufacturer to be in the range of 365 to 375 degrees C. The synthetic oils used in the engine had auto-ignition temperatures as low as 280 degrees C. A comparison of these temperatures indicates the potential for auto-ignition, and given that there were no other ignition sources identified, it was likely the leaking oil auto-ignited when it atomized on entry into the buffer space and resulted in an internal oil fire. About 10 seconds before the engine failure, the fire breached the front face of the HP-IP bearing chamber buffer space and impinged directly on the HP-IP triple seals. The intense heating distorted the seals, causing them to come into contact with each other. The design of the engine was such that the pressure within the buffer space and behind the IP turbine was lower than the hot annulus gas airstream exiting the HP turbine. This meant that when the triple seals were breached, those hot gases were drawn into the space behind the HP turbine disc. Openings in the hub at the rear of the buffer space directed intense radiant heat and flame onto the triple seal at the rear of the HP-IP bearing chamber. The triple seal failed and the flame was then directed into the IP turbine drive arm. The IP turbine drive arm rapidly heated, reducing the strength of the material, resulting in an overstress failure separating the IP turbine from the IP drive shaft. Immediately after the IP disc separated from the drive shaft, there was a rapid reduction in the IP and LP compressor speeds, but only a small reduction in the HP assembly speed. As the rotational speed increased, the stresses within the IP disc increased, and 4 seconds after its separation from the drive arm, the disc material failed and the disc burst.